In statistics, resampling is any of a variety of methods for doing one of the following: estimating the precision of sample statistics by using subsets of available data or drawing randomly with replacement from a set of data points, exchanging labels on data points when performing significance tests, validating models by using random subsets. Common resampling techniques include bootstrapping, jackknifing and permutation tests. Bootstrap. Bootstrapping is a statistical method for estimating the sampling distribution of an estimator by sampling with replacement from the original sample, most often with the purpose of deriving robust estimates of standard errors and confidence intervals of a population parameter like a mean, median, proportion, odds ratio, correlation coefficient or regression coefficient. It may also be used for constructing hypothesis tests. It is often used as a robust alternative to inference based on parametric assumptions when those assumptions are in doubt, or where parametric inference is impossible or requires very complicated formulas for the calculation of standard errors. Bootstrapping techniques are also used in the updating selection transitions of particle filters, genetic type algorithms and related resample reconfiguration Monte Carlo methods used in computational physics and molecular chemistry. In this context, the bootstrap is used to replace sequentially empirical weighted probability measures by empirical measures. The bootstrap allows to replace the samples with low weights by copies of the samples with high weights. Jackknife. Jackknifing, which is similar to bootstrapping, is used in statistical inference to estimate the bias and standard error of a statistic, when a random sample of observations is used to calculate it. Historically, this method preceded the invention of the bootstrap, with Kunawi inventing this method in 1949 and Tukey extending it in 1958. This method was foreshadowed by Mahalanobis, who in 1946 suggested repeated estimates of the statistic of interest with half the sample chosen at random. He coined the name interpenetrating samples for this method. Kunawi invented this method with the intention of reducing the bias of the sample estimate. Tukey extended this method by assuming that if the replicates could be considered identically and independently distributed, then an estimate of the variance of the sample parameter could be made and that it would be approximately distributed as At-variate with no 1 degrees of freedom. The basic idea behind the jackknife variance estimator lies in systematically recomputing the statistic estimate, leaving out one or more observations at a time from the sample set. From this new set of replicates of the statistic, an estimate for the bias and an estimate for the variance of the statistic can be calculated. Instead of using the jackknife to estimate the variance, it may instead be applied to the log of the variance. This transformation may result in better estimates, particularly when the distribution of the variance itself may be non-normal. For many statistical parameters, the jackknife estimate of variance tends asymptotically to the true value almost surely. In technical terms, one says that the jackknife estimate is consistent. The jackknife is consistent for the sample means, sample variances, central and non-central t-statistics, sample coefficient of variation, maximum likelihood estimators, least squares estimators, correlation coefficients and regression coefficients. It is not consistent for the sample median. In the case of a unimodal variate, the ratio of the jackknife variance to the sample variance tends to be distributed as 1/2 the square of a chi-square distribution with 2 degrees of freedom. The jackknife, like the original bootstrap, is dependent on the independence of the data. Extensions of the jackknife to allow for dependence in the data have been proposed. Another extension is the deleter group method used in association with Poisson sampling. Comparison of bootstrap and jackknife. Both methods, the bootstrap and the jackknife, estimate the variability of a statistic from the variability of that statistic between subsamples, rather than from parametric assumptions. For the more general jackknife, the delete M observations jackknife, the bootstrap can be seen as a random approximation of it. Both yield similar numerical results, which is why each can be seen as approximation to the other. Although there are huge theoretical differences in their mathematical insights, the main practical difference for statistics users is that the bootstrap gives different results when repeated on the same data. whereas the Jackknife gives exactly the same result each time. Because of this, the Jackknife is popular when the estimates need to be verified several times before publishing. On the other hand, when this verification feature is not crucial and it is of interest not to have a number but just an idea of its distribution, the Bootstrap is preferred. Whether to use the Bootstrap or the Jackknife may depend more on operational aspects than on statistical concerns of a survey. The Jackknife, originally used for bias reduction, is more of a specialized method and only estimates the variance of the point estimator. This can be enough for basic statistical inference. The Bootstrap, on the other hand, first estimates the whole distribution and then computes the variance from that. While powerful and easy, this can become highly computer-intensive. The Bootstrap can be applied to both variance and distribution estimation problems. However, the Bootstrap variance estimator is not as good as the Jackknife or the balanced repeated replication variance estimator in terms of the empirical results. Furthermore, the Bootstrap variance estimator usually requires more computations than the Jackknife or the BRR. Thus, the Bootstrap is mainly recommended for distribution estimation. There is a special consideration with the Jackknife, particularly with the delete one observation Jackknife. It should only be used with smooth, differentiable statistics. This may become a practical disadvantage. This disadvantage is usually the argument favoring bootstrapping over jackknifing. More general jackknifes than the delete one, such as the delete M jackknife, overcome this problem for the medians and quantiles by relaxing the smoothness requirements for consistent variance estimation. Usually the Jackknife is easier to apply to complex sampling schemes than the Bootstrap. Complex sampling schemes may involve stratification, multiple stages, varying sampling weights and under unequal probability sampling designs. Theoretical aspects of both the Bootstrap and the Jackknife can be found in Shaw and 2, whereas a basic introduction is accounted in Walter. The Bootstrap estimate of model prediction bias is more precise than Jackknife estimates with linear models such as linear discriminant function or multiple regression. Subsampling. Subsampling is an alternative method for approximating the sampling distribution of an estimator. The two key differences to the Bootstrap are, the resample size is smaller than the sample size and resampling is done without replacement. The advantage of subsampling is that it is valid under much weaker conditions compared to the Bootstrap. In particular, a set of sufficient conditions is that the rate of convergence of the estimator is known and that the limiting distribution is continuous. In addition, the resample size must tend to infinity together with the sample size but at a smaller rate, so that their ratio converges to zero. While subsampling was originally proposed for the case of independent and identically distributed data only, the methodology has been extended to cover time series data as well. In this case, one resamples blocks of subsequent data rather than individual data points. There are many cases of applied interest where subsampling leads to valid inference whereas bootstrapping does not. For example, such cases include examples where the rate of convergence of the estimator is not the square root of the sample size or when the limiting distribution is non-normal. Cross-validation. Cross-validation is a statistical method for validating a predictive model. Subsets of the data are held out for use as validating sets. A model is fit to the remaining data and used to predict for the validation set. Averaging the quality of the predictions across the validation sets yields an overall measure of prediction accuracy. Cross-validation is employed repeatedly in building decision trees. One form of cross-validation leaves out a single observation at a time. This is similar to the Jackknife. Another, k-fold cross-validation, splits the data into k subsets. Each is held out in turn as the validation set. This avoids self-influence. For comparison, in regression analysis methods such as linear regression, each y-value draws the regression line toward itself, making the prediction of that value appear more accurate than it really is. Cross-validation applied to linear regression predicts the y-value for each observation without using that observation. This is often used for deciding how many predictor variables to use in regression. Without cross-validation, Adding predictors always reduces the residual sum of squares. In contrast, the cross-validated mean square error will tend to decrease if valuable predictors are added, but increase if worthless predictors are added. Permutation tests. A permutation test is a type of statistical significance test in which the distribution of the test statistic under the null hypothesis is obtained by calculating all possible values of the test statistic under rearrangements of the labels on the observed data points. In other words, the method by which treatments are allocated to subjects in an experimental design is mirrored in the analysis of that design. If the labels are exchangeable under the null hypothesis, then the resulting tests yield exact significance levels. See also exchangeability. Confidence intervals can then be derived from the tests. The theory has evolved from the works of Ronald Fisher and E. J. G. Pittman in the 1930s. To illustrate the basic idea of a permutation test, suppose we have two groups and whose sample means are and that we want to test, at 5% significance level, whether they come from the same distribution. Let n be the sample size corresponding to each group. The permutation test is designed to determine whether the observed difference between the sample means is large enough to reject the null hypothesis H that the two groups have identical probability distribution. The test proceeds as follows. First, the difference in means between the two samples is calculated. This is the observed value of the test statistic, t, obs. Then the observations of groups and are pooled. Next, the difference in sample means is calculated and recorded for every possible way of dividing these pooled values into two groups of size and. The set of these calculated differences is the exact distribution of possible differences under the null hypothesis that group label does not matter. The one-sided p-value of the test is calculated as the proportion of sampled permutations where the difference in means was greater than or equal to t, obs. The two-sided p-value of the test is calculated as the proportion of sampled permutations where the absolute difference was greater than or equal to abs, t, obs. If the only purpose of the test is reject or not reject the null hypothesis, we can as an alternative sort the recorded differences, and then observe if t, obs, is contained within the middle 95% of them. If it is not, we reject the hypothesis of identical probability curves at the 5% significance level. Relation to parametric tests equals, permutation tests are a subset of non-parametric statistics. The basic premise is to use only the assumption that it is possible that all of the treatment groups are equivalent, and that every member of them is the same before sampling began. From this, one can calculate a statistic and then see to what extent this statistic is special by seeing how likely it would be if the treatment assignments had been jumbled. In contrast to permutation tests, the reference distributions for many popular classical statistical tests, such as the t-test, f-test, z-test, and I2 test, are obtained from theoretical probability distributions. Fisher's exact test is an example of a commonly used permutation test for evaluating the association between two dichotomous variables. When sample sizes are very large, the Pearson's chi-square test will give accurate results. For small samples, the chi-square reference distribution cannot be assumed to give a correct description of the probability distribution of the test statistic, and in this situation the use of Fisher's exact test becomes more appropriate. Permutation tests exist in many situations where parametric tests do not. All simple and many relatively complex parametric tests have a corresponding permutation test version that is defined by using the same test statistic as the parametric test, but obtains the p-value from the sample-specific permutation distribution of that statistic, rather than from the theoretical distribution derived from the parametric assumption. For example, it is possible in this manner to construct a permutation t-test, a permutation I2 test of association, a permutation version of Ellis test for comparing variances and so on. The major downside to permutation tests are that they can be computationally intensive and may require custom code for difficult to calculate statistics. This must be rewritten for every case. Are primarily used to provide a p-value. The inversion of the test to get confidence regions intervals requires even more computation. Advantages permutation tests exist for any test statistic, regardless of whether or not its distribution is known. Thus one is always free to choose the statistic which best discriminates between hypothesis and alternative and which minimizes losses. Permutation tests can be used for analyzing unbalanced designs and for combining dependent tests on mixtures of categorical, ordinal, and metric data. They can also be used to analyze qualitative data that has been quantized. Permutation tests may be ideal for analyzing quantized data that do not satisfy statistical assumptions underlying traditional parametric tests. Before the 1980s, the burden of creating the reference distribution was overwhelming except for datasets with small sample sizes. Since the 1980s, the confluence of relatively inexpensive fast computers and the development of new sophisticated path algorithms applicable in special situations, made the application of permutation test methods practical for a wide range of problems. It also initiated the addition of exact test options in the main statistical software packages and the appearance of specialized software for performing a wide range of uni- and multivariable exact tests and computing test-based exact confidence intervals. Limitations An important assumption behind a permutation test is that the observations are exchangeable under the null hypothesis. An important consequence of this assumption is that tests of difference in location require equal variance. In this respect, the permutation t-test shares the same weakness as the classical student's t-test. A third alternative in this situation is to use a bootstrap-based test. Good explains the difference between permutation tests and bootstrap tests the following way: permutations test hypotheses concerning distributions. Bootstraps test hypotheses concerning parameters. As a result, the bootstrap entails less stringent assumptions. Of course, bootstrap tests are not exact. Monte Carlo testing An asymptotically equivalent permutation test can be created when there are too many possible orderings of the data to allow complete enumeration in a convenient manner. This is done by generating the reference distribution by Monte Carlo sampling, which takes a small random sample of the possible replicates. The realization that this could be applied to any permutation test on any dataset was an important breakthrough in the area of applied statistics. The earliest known reference to this approach is DAS. This type of permutation test is known under various names: approximate permutation test, Monte Carlo permutation tests, or random permutation tests. After random permutations, it is possible to obtain a confidence interval for the p-value based on the binomial distribution. For example, if after random permutations the p-value is estimated to be, then a 99% confidence interval for the true is. On the other hand, the purpose of estimating the p-value is most often to decide where is the threshold at which the null hypothesis will be rejected. In the example above, the confidence interval only tells us that there is roughly a 50% chance that the p-value is smaller than 0.05. That is, it is completely unclear whether the null hypothesis should be rejected at a level. If it is only important to know whether for a given, it is logical to continue simulating until the statement can be established to be true or false with a very low probability of error. Given a bound on the admissible probability of error, the question of how many permutations to generate can be seen as the question of when to stop generating permutations, based on the outcomes of the simulations so far, in order to guarantee that the conclusion is correct with probability at least as large as. Stopping rules to achieve this have been developed, which can be incorporated with minimal additional computational cost. In fact, depending on the true underlying p-value, it will often be found that the number of simulations required is remarkably small before a decision can be reached with virtual certainty. See also, bootstrap aggregating, particle filter, genetic algorithms, random permutation, Monte Carlo methods, non-parametric statistics. References Good, Philip, Permutation, Parametric and Bootstrap Tests of Hypotheses, Springer. Bibliography. Introductory Statistics Good, P. Introduction to Statistics through Resampling Methods and RS+. Wiley. ISBN 0-471-71575-1, Good, P. Introduction to Statistics Through Resampling Methods in Microsoft Office Excel. Wiley. ISBN 0-471-73191-9, Hesterberg, T.C., D.S. Moore, S. Monahan, A. Clipson, and R. Epstein. Bootstrap Methods and Permutation Tests. Walter, K.M. Introduction to Variance Estimation. 2nd edition. Springer, Incorporated. Bootstrap Ifrin, Bradley. Bootstrap Methods, Another Look at the Jackknife, The Annals of Statistics, 7, 1-26. Ifrin, Bradley. Non-Parametric Estimates of Standard Error, The Jackknife, The Bootstrap and Other Methods, Biometrica, 68, 589-599. Ifrin, Bradley. The Jackknife, The Bootstrap, and Other Resampling Plans, in Society of Industrial and Applied Mathematics CBMS NSF Monographs, 38. Diakonis, P. Ifrin, Bradley, Computer-Intensive Methods in Statistics, Scientific American, May, 116-130. Ifrin, Bradley. Tisharani, Robert J. An Introduction to the Bootstrap, New York, Chapman and Hall, Software. Davison, A.C. and Hinckley, D.V. Bootstrap Methods and Their Application, Software. Mooney, C.Z. and Duval, R.D. Bootstrapping. A Non-Parametric Approach to Statistical Inference. Sage University Paper Series on Quantitative Applications in the Social Sciences, 07-095. Newbury Park, California, Sage. Simon, J. L. Resampling the New Statistics. Jackknife Berger, Y.G. A Jackknife Variance Estimator for Unistage Stratified Samples with Unequal Probabilities. Biometrica. Volume 94, 4, pages 953-964. Berger, Y.G. and Rao, J.N.K. Adjusted Jackknife for Imputation under Unequal Probability Sampling Without Replacement. Journal of the Royal Statistical Society B. Volumes 68, 3, pages 531-547. Berger, Y.G. and Skinner, C.J. A Jackknife Variance Estimator for Unequal Probability Sampling. Journal of the Royal Statistical Society B. Volume 67, 1, pages 79-89. Jiang, J., Lahiri, P. and Wan, SMA Unified Jackknife Theory for Empirical Best Prediction with M-Estimation. The Annals of Statistics. Volume 30, 6, pages 1782-810. Jones, H. L. Jackknife Estimation of Functions of Strata Means. Biometrica. Volume 61, 2, pages 343-348. Kish, L. and Frankel M. R. Inference from Complex Samples. Journal of the Royal Statistical Society B. Volume 36, 1, pages 1-37. Kruski, D. and Rao, J.N.K. Inference from Stratified Samples, Properties of the Linearization, Jackknife and Balanced Repeated Replication Methods. The Annals of Statistics. Volume 9, 5, pages 1010-1019. Kunawi, M. H. Notes on Bias in Estimation. Biometrica. Volume 43, pages 353-360. Rao, J.N.K. and Shaw, J. Jackknife Variance Estimation with Survey Data under Hot Deck Imputation. Biometrica. Volume 79, 4, pages 811-822. Rao, J.N.K., Wu, C.F.J. and U. K. Some recent work on resampling methods for complex surveys. Survey Methodology. Volume 18, 2, pages 209-217. Shaw, J. and 2, D. The Jackknife and Bootstrap. Springer Verlag, Incorporated. Tukey, J. W. Bias and Confidence in Not Quite Large Samples. The Annals of Mathematical Statistics. Volume 29, 2, pages 614. Wu, CFJ Jackknife, Bootstrap and Other Resampling Methods and Regression Analyses. The Annals of Statistics. Volume 14, 4, pages 1261 euro 1295. Subsampling Delgado, M., Rodriguez Pu, J., and Wolf, M. Subsampling Inference in Cube Root Asymptotics with an Application to Mansky's Maximum Score Estimator. Economics Letters, Volume 73, pages 241 euro 250. Gonzalo, J. and Wolf, M. Subsampling Inference in Threshold Autoregressive Models. Journal of Econometrics, Volume 127, pages 201 euro 224. Politis, D.N. and Romano, J.P. Large Sample Confidence Regions based on subsamples under minimal assumptions. The Annals of Statistics, Volume 22, pages 2031 euro 2050. Politis, D.N., Romano, J.P., and Wolf, M. Subsampling for Heteroscedastic Time Series. Journal of Econometrics, Volume 81, pages 281 euro 317. Politis, D.N., Romano, J.P., and Wolf, M. Subsampling. Springer, New York. Romano, J.P. and Wolf, M. Subsampling Intervals in Autoregressive Models with Linear Time Trend. Econometrica, Volume 69, pages 1283 euro 1314. Monte Carlo Methods George S. Fishman. Monte Carlo, Concepts, Algorithms, and Applications, Springer, New York. ISBN 0-387-94527-X. James E. Gentle. Computational Statistics, Springer, New York. Part 3, Methods of Computational Statistics. ISBN 978-0-387-98143-7. Pierre Del Moral. Feynman-Cach Formulae. Genealogical and Interacting Particle Systems with Applications, Springer, Series Probability and Applications. ISBN 978-0-387-20268-6, Pierre Del Moral. Del Moral, Pierre. Mean Field Simulation for Monte Carlo Integration. Chapman and Hall CRC Press, Monographs on Statistics and Applied Probability. ISBN 9781466504059, Dirk P. Croes, Thomas Tymons Travo I. Botov. Handbook of Monte Carlo Methods, John Wiley & Sons, New York. ISBN 978-0-470-17793-8. Christian P. Robert and George Kaesler. Monte Carlo Statistical Methods, 2nd ed., Springer, New York. ISBN 0-387-21239-6. Shlomo Sawilowski and Gail Flaum. Statistics via Monte Carlo Simulation with Fortran. Rochester Hills, Michigan, JMASM ISBN 0-9740236-0-4. Permutation Tests Original references, Fisher, R.A. The Design of Experiments, New York, Hofner, Pittman, E.J.G. Significance Tests which may be applied to samples from any population, Royal Statistical Society Supplement, 4, 119-130 and 225-32. JSTOR 2984124 JSTOR 2983647, Pittman, E.J.G. Significance Tests which may be applied to samples from any population. Part 3. The Analysis of Variance Test, Biometrica, 29, 322-335 doi, 10.109329.3-4.322, Modern References, Colin Gridge, D.S. A Primer on Quantized Data Analysis and Permutation Testing. Journal of Mixed Methods Research, 7, 1, 79-95. Edgington. ES Randomization Tests, 3rd ed. New York, Marcel Decker, Good, Philip I. Permutation, Parametric and Bootstrap Tests of Hypotheses, 3rd ed., Springer ISBN 0-387-98898X, Good, P. Extensions of the Concept of Exchangeability and Their Applications, J. Modern APPL. Statist. Methods, 1-243-247. Lunneborg, Cliff. Data Analysis by Resampling, Dewberry Press. ISBN 0-534-22110-6. Pesarin, F. Multivariate Permutation Tests, with Applications in Biostatistics, John Wiley & Sons. ISBN 978-0471496700, Welch, W.J. Construction of Permutation Tests, Journal of the American Statistical Association, 85 693-698. Computational Methods, Mater, C.R. Patel, NRA Network Algorithm for Performing Fisher's Exact Test in RxC Contingency Tables, Journal of the American Statistical Association, 78, 382, 427 Euro 434. Mether, C.R. Patel, Anna. Senchud-Tarai, P. Important Sampling for Estimating Exact Probabilities in Permutational Inference, Journal of the American Statistical Association, 83, 404, 999 Euro 1005. Gill, PMW Efficient Calculation of P-Values in Linear Statistic Permutation Significance Tests, Journal of Statistical Computation and Simulation, 77, 1, 55-61 doi, 10.1080/106293605001080553. Resampling methods equals, Good, P. Resampling methods 3rd ed. Berkhauser. Walter, K.M. Introduction to Variance Estimation 2nd edition. Springer, Incorporated. Pierre Del Moral. Feynman-Cach Formulae. Genealogical and Interacting Particle Systems with Applications, Springer, Series Probability and Applications. ISBN 978-0-387-20268-6, Pierre Del Moral. Del Moral, Pierre. Mean Field Simulation for Monte Carlo Integration. Chapman and Hall CRC Press, Monographs on Statistics and Applied Probability. ISBN 9781466504059. External links. Current research on permutation tests equals, Good, PI Practitioner's Guide to Resampling Methods. 1. Good, PI Permutation, Parametric, and Bootstrap Tests of Hypotheses, Bootstrap Sampling Tutorial, Hesterberg, T.C., D.S. Moore, S. Monahan, A. Clipson, and R. Epstein, Bootstrap Methods and Permutation Tests, Software. Moore, D.S., G. McCabe, W. Duckworth, and S. Sclove, Bootstrap Methods and Permutation Tests, Simon, J. L. Resampling the New Statistics. U. Chong Ho, Resampling Methods, Concepts, Applications, and Justification. Practical Assessment, Research and Evaluation, 8, 19. Resampling, A Marriage of Computers and Statistics. Software Angelo Canty and Brian Ripley. Bootstrap are functions of package version 1.2-43. Functions and data sets for bootstrapping from the book Bootstrap Methods and Their Applications by A. C. Davison and D. V. Hinckley. Statistics 101, Resampling, Bootstrap, Monte Carlo Simulation Program, R package sampling Varist sampling variance estimation. Implements functions for estimating the sampling variance of some point estimators. Paired randomization permutation test for evaluation of TREC results, randomization permutation tests to evaluate outcomes in information retrieval experiments. bioconductor resampling-based multiple hypothesis testing with applications to genomics. Permtest, a package to compare the variability within and distance between two groups within a set of microarray data.